Hey, what's up, guys? This is Chung here again. So today's daily challenge problem, right? Number 51, unqueens. Right. So this one is a very classic problem. As you can see, has a very small like numbers here, right? So basically, uh, the unqueen puzzle is a problem of placing unqueens on an n times n chessboard, such that no two queens attack each other. Okay, it's pretty straightforward, right? So basically, you're given like an integer n and return all the distinct solutions, to the n queens puzzle. And every solution contains a distinct board configuration of n queens, right? Where q represents the queen and dot means no queens at that position. So for example, right, so for this one, we have like size n chessboard, and there are like two distinct solutions for this. Right, so for those who are not familiar with chess, basically a queen, if you place a queen at a certain location, basically the queen can attack both the same row, the same column, and the same diagonal and the same anti-diagonal. That's the range this queen can reach, right? And we need to find like all the solutions that basically each queen cannot attack each other. So that's a problem, right? And for this one, we have two answers here, and we return this kind of each like configurations as like a string, represents a row, right? There are like 4 rows here. Cool. So constraint is 9, basically at maximum 9 chessboard, right? So this very obviously it's a backtracking problem, right? Basically, at each state we have to place a queen on this one, and then we just try each of the location, right? And then we just backtrack. And so how can we backtrack? I mean, a brutal force way will be what? So at each, basically, obviously, we're gonna have like we need to have like several like status like parameters to record the current available rows. What are the rows that are currently available, and what are the rows that columns are available, and also the anti-diagonal and diagonals and anti-diagonals. Basically, normally we need 4 like variables to store the status for the current state, right? And at each of the state, basically we try to place the queen at each of the location. And if we do that, right? If we do that, actually, we have what? So basically, because we at each of the state we'll have like let's say we have like n uh we have n size chessboard, so the total cell will be n square, right? And if we at each of the state we try to place it on each of the state, it's going to be n square of the power of n square, right? Obviously this one will TLE, because let's say with a size 9 we'll have 81, right? 81 of the power of 81. So this one obviously it will TLE. So which means we cannot just try to place this queen at each of the cell every time. So what we can do is that we can try to place a queen based on the rows or based on the columns. It doesn't really matter, because basically I so the reason we can do that is because since we have n queens we need to place, and we have a size n chessboard. It means that regardless of the final result, each row must have a queen. It could be at the first column, it could be at the second column. It doesn't really matter, right? So what it means is that as long as we place a queen on a certain row, then it means that we can ignore the current row. We can move to the next one, because obviously there's no way we can place 2 queens on the same row. That's why we only have to loop through the columns. instead of each cell, right? In that case, actually, instead of this time complexity, we'll have like n factorial time complexity, right? Because at the first loop, we have like n columns. N columns we need to check, right? Basically, we have n possible places we can place our queen, right? And on the second one, since one of the columns have already been placed, so which means that we can only place our queen on the remaining columns, right? Which is so n times n minus 1, and then n times n minus 2, so on and so forth until there's only one left. Yep. So that's it, right? I mean, that's how we do the backtracking here. Okay, so let's do the backtracking then. Backtrack. Now, I'm going to since the parameters will be I here, right? And it means that on each row will be placed a coin. And like I said, we're gonna need a few like global variables to help us track the status of the columns and the diagonals. So for the columns, we're gonna have like a false at the beginning, right? So which means we can place any column at the beginning. And then we need the diagonals, right? Going to be, for the diagonals, everyone knows that, it's going to be the key for the diagonals one is going to be I plus j, right? And for the key of anti-diagonal is the I minus j. That's the two keys for the diagonal and anti-diagonal. So in order to do this, instead of using like array here, I'm going to use a dictionary here because the key could be a negative or greater than n here. That's why I'm going to have a default dictionary of Boolean, right? Same thing for anti-diagonal. Same thing, default dictionary of Boolean. And then we have the final answer. It's going to be this. And yeah, let's do a quiz here. We need a chessboard basically to update, right? So at the beginning, everything is a dot, right? And we just initiate an empty chessboard basically, and then we do a backtrack, right? Backtrack, we start from the first row, and then in the end we return the answer. So that's the setup for this backtrack. So here, if I is equal to n, right? So it means that we have reached we have placed the queen for each row. It means that we have successfully find like a solution, and it means that we just need to append this solution to the answer, right? So what we can do is that we can just make a copy of this of the row, because a row is also an array, but we need a string. That's why we have to do a join here, right? Join of row for row in queens, right? Or let's call it boards. Yeah, board. How about this? A board is better. It's a better name, I guess. Yep. So and then we return here. Okay. Otherwise, we try to place. Otherwise, basically, we try to place a queen at ith row, right? Basically, we try to place a queen at ith row, right? Because we're at ith row here. But where, right? We have n options here, right? It could be anywhere, right? That's why we need to check if the not columns j, right? If the columns is not occupied and the diagonal is not occupied, right? So I plus j and not the anti-diagonal is not occupied, right? I minus j. If everything is fine, then we can place the queen at the current row, right? Where it's I and j, right? I and j equals to the q in this case, right? And then after that, we update the columns and the diagonals, right? Then we recursively go to the next row, right? It's going to be I plus 1. And then what do? We backtrack, right? We set everything back to where it was, right? To what it was, because if we next time if we try to place like this queen on this different column, it will not be affected by the previously for loop, right? It's a very standard backtracking thing. Yep. So that's it, right? We backtrack, right? That's it. So if I run the code, accept it, right? Submit. There you go. Yep. So that's the problem, right? I mean, that's the solution. And time complexity, like I said, n factorial, right? Cool. Yeah, I think that's it, right? I mean, it's a very classic backtracking problem, right? Oh, and the reason we cannot use a DP to solve this one is because because at the beginning I was thinking about, can we use something like a DP? Basically we can cache something like this, right? So we can remember the state, so we can reuse the state later on. But for this problem, it's a little bit different, because at each state, we will have like this board, right? We're not uh, asking to calculate the number. I mean, how can I say it? The total number of the solutions. We're asking. We're being asked to get the actual board. That's why we cannot use like DP, since in the end what we really need is to append this answer to append the current board to the answer. That's why there's no way we can use a DP here. Instead, it's just like a purely backtracking problem. Yep, I think that's it, right? Cool. I'll stop here then. All right, thank you for watching the video, guys, and stay tuned. See you guys soon. Bye bye.